Hello, everyone. This is Lee Wing, and my partners are Tyson and Kyle and Daniel. And so our project is the deep learning model for Q&A system. So let's get started. Our main object is using a question and answering system. This system is one of the most important NLP tasks, and it provides a direct correlation to systems' natural language understanding ability. This also analyzes the challenges that involves in reading comprehensions and answering any questions. This also analyzes the neural network model using what we call the pre-trained BERT model. So we'll be comparing with the different neural network models and combine the different models using the sampled method to test the overall performance. So the database that we use is the Squad, as known as Stanford question answering dataset. This is pretty interesting because this dataset consists of pairs of 100,000 questions and answers, which is really big. And all these data came from Wikipedia articles. It's not like specific articles. It's like very diverse topics, like any topics, and it compares the performance of different models using a standard data set, which also maintains a leaderboard.
The first thing we did with the Stanford question answering dataset is that we wanted to analyze the text itself to learn more about it. As you can see in the screenshot of our code below, we begin by importing the NLTK and the sentence and word tokenizers. We also chose to utilize the punkt package from the Knowledge Language Toolkit. We tokenize the text first into sentences, then we tokenize them into individual words. Now that we have tokenized the data, we want to continue the data pre-processing phase. To do this, we are going to clean the text by making it all lowercase, removing stop words, getting rid of punctuation, and removing any non-alphabetical characters. As you can see in the screenshot of our code below, we use several functions that are found in the NLTK package, such as lower and stop words.
So I'm going to talk about our unigrams and bigrams in the Squad dataset. So of the types and questions that we took, the top 20 words after removing the stop words are shown in the graph to the left. A lot of them are just about the geography of the world, pretty general topics such as bells, states, music, millions, seasons, something similar. On the right, you have bigrams. Again, it has a lot to do with geographical locations like New York. Then you have New York City, American Idol, Dalai Lama, United Kingdom, Hong Kong. So stuff that we see on a daily basis that people would most likely want to know the answers for and would be a part of a lot of questions. So continuing on our analysis for the bigrams of the Squad dataset, you see that we applied the frequency filter of 2 to the bigrams and use the score of the n-grams for our frequency numbers. You can see that a lot of the most frequent are based on history and geographical, such as United States, World War, Soviet Union. You can see there's War II based on World War II. So you can see a lot of these questions are based on United States history and maybe just global history in general. On the right, you see we applied the frequency filter of 5 and just got the PMI of some bigrams. These are the 25th to 40th ranked. Again, there's a lot of diverse bigrams, so you see a lot about history, like the Viet Cong, the Vietnam War, Iwo Jima, but you also have like entertainment stars such as Sylvester Stallone and Britney Spears. So you can see that this data set is very diverse. So the next thing I'm going to talk about is the sentiment polarity. The next So the next thing I'm going to talk about is the sentiment polarity distribution. We use the text blob packages in Python, which gives a polarity score from -1 to 1 based on the tokenized sentences. As you can see on the graph on the right, most of the sentences had a neutral polarity, but you can see more of them had a positive polarity than negative, which shows that the questions and answers tend to be more of positive, which makes sense because people like to ask positive statements. You can see some of them with the highest polarity is you are now watching the greatest living rock star on the planet. A lot of them have like the greatest or the best or awarded or impressed, or just positive words that speak to how accurate this polarity actually was. The next analysis that we conducted is a sentiment analysis. We used the sentiment polarity corpus to train the classifier, similar to the one that we used in class. Then we used the classifier to give a positive and negative sentences, give a label to the positive and sentences negative to all of the questions and answers in the data set. This specifically looks at a question about Beyonce, an answer about her. So you can see there's about how she won Grammy Awards, how she's the most powerful female musician, stuff that is positive about her life. And so for our last piece about sentiment analysis, we have a list of the negative sentences that were labeled in the question and answer set about Beyonce. You can see that some of the sentences below talk about some of Beyonce's hardships in life, such as her depression and the fact that she had some hardships growing up because her family's income was cut in half. This shows that the classifier, the sentiment polarity corpus, sentence polarity corpus worked as planned, and is a good way to see sentiment analysis. In this case, was a good way to see the how each question was laid out.
So what is the BERT model? The BERT, also known as the bidirectional encoder representation from transformers model, it's one of the new kind of NLP model framework. This model is pre-trained through deep bidirectional representation, and it contains fine-tuned output layer for different kinds of NLP tasks, which is mostly used for transfer learning, and it uses the attention model to solve multiple tasks, and this model performs much better than other similar deep learning models.
So how does a BERT model work? The BERT model uses a modified transformer network. The original transformer network has both encoder and decoder, which has an attention layer in between, but the modified transformer network has just the encoder part and the attention layer, which is then fed as an output from the BERT model. So the main goal of the BERT model is to capture the language modeling. So it makes a deeper sense of the language context. So only the encoder mechanism is used. So how does it capture the encoder mechanism? So it basically uses a bidirectional approach where it reads the entire sentence of sequence of words instead of sequentially reading the data. So it basically learns the context of words based on all its surroundings. In our task, we use a pre-trained BERT model, which is trained on two separate tasks, that is next sentence prediction and masked word sentence. The next sentence prediction basically consists of a task where two sentences are passed in, and the model checks if the second sentence is part of the first sentence. And in the masked word sentence, we input a sentence with the word masked, and the model has to predict what that masked word is. So based on these two pre-trained tasks, the BERT model captures the language modeling of the sentences. This helps us in our scenario where we have to capture the story and the question to figure out the exact answer for that task. So the BERT model basically gets input of story and question, and it outputs basically the vectors that says what kind of relationship it's there between the story and question. Based on that, our output layer, which is a custom layer, figures out what should be the start position and what should be the end position for the answer to the question. We have designed two separate models, one which uses basically a dense layer stack on top of BERT model, and the second model uses a dense layer and endless time layer to capture both start and end positions. The image on the right shows The image on the right shows a custom BERT model output from TensorFlow Keras. Here we need to pass the input as a pre-processed tokenized vectors from the BERT tokenizer. Basically, it converts the input sentence into token numbers that is specific to the embedding layer of the BERT model. Here, the story sentence and question sentence is passed as a single input value separated by special tokens, and the length is limited to 384 size. The output is basically a vector of values which is passed with softmax layer and predicted as start and end vector of the answers. Memory networks is another Memory networks is another neural network we're trying to compare with the BERT model. So this is also similar to an attention model that is used in BERT, but the neural network architecture is a bit different. Here we pass in the story in question as again an embedded vector which is tokenized, and the story is stored in the memory as input memory representation. This is then passed with along with the question as the output memory representation, and then the sum of these is basically used to capture the end answer that is supposed to be for that specific question. So the memory network basically is a sort of similar to BERT, but then the representation of the memory is a bit different. Also, the final output layer is a dense layer which outputs the embedding vector of the answer instead of the position of the answer. The image on the right shows the next the image on the right shows a structure of memory network from the output of TensorFlow Keras. Here, the input sentences are tokenized during the pre-processing task, and the token size is basically limited to 11,000. The story sentence and question sentence are also limited in size of 63 and 38. Here, the limit of length is basically due to the size of the memory network. A larger size in the length of the story sentence and question sentence lead to a larger size of the memory network, and which in turn has an impact on the performance of the network. Also, the number of token size would increase the output dense layer values that has to be computed, because unlike the BERT model, the memory network model provides a embedding vector of the word instead of the position of the word. So the position of the start word is not said, but the embedding vector of the answer is provided as output. So this has direct performance impact on memory networks, and the number of trainable parameters also is much less compared to the BERT model. The next model is a modification of the previous memory network, but with the additional use of glove embedding. Glove embedding is basically a word representation model which is pre-trained and which can capture the similarity of words. So instead of using the model itself to figure out the similarity of words of story and the question, we are using the glove vectors. So this is basically used in the embedding layer where the glove weights are basically passed to the model and they're frozen during training. And the input values of story and the question is basically tokenized based on this glove embedding, and it's a dimension of 300 compared to a dimension of 100 that was used in the previous model. And the rest of the model is kept as similar as the previous one, and it has the similar trainable parameters of the output layer as well as a memory network layer. The last neural network is the last neural network is basically used as a baseline performance. So here we use a old LSTM model where it captures the semantics of the input sequence. Here we have two separate LSTM models which are being passed from the embedding layers, and they both capture the sentence features, and the output of the LSTM layers are then concatenated and passed to the dense layer, and the dense layer basically outputs the vector of the answer that is supposed to be there for the story and the question. Unlike the BERT model, again this model uses the value of the word instead of the start position and end position. Next, we compare the performance of the BERT model with different hyperparameter values. The image on the right shows the loss of training and loss of validation for the models. Here we try different learning rates for the model. A lower learning rate would make the model change update values much lesser compared to the learning rate with having higher values, and the number of epochs is basically governs how many times does the data set have to be passed again and again to the model so that it learns features, and the optimizer basically governs the way at which it converges. So changes to these have direct impact on the performance. So tuning of this is critically important for BERT and other models. Finally, we'll see the comparison of the LSTM and memory networks. The below graphs basically show the different loss and accuracy values for the train and validation dataset. Here we can see that memory networks with glove embeddings have much better performance compared to the LSTM and the basic memory networks. The main reason is because the glove embeddings are capturing the semantics of the words much better since it was trained on a much larger dataset size and thus can capture the semantics. Some of the challenges we faced during the creation of the models was the vocabulary size, which has direct impact on the performance. Smaller vocabulary size actually performed much better for the LSTM and memory networks. This, we think, was a cause of the larger vocabulary size increasing the number of possible outputs for the model. Also, we found that the BERT model had a large set of parameters, and training this was a challenge because a model would not load into the memory space of the system and would crash. So this leads to training of a smaller BERT model, which was fine tuned to just squad dataset. So the performance led to a much lesser compared to the original approach, and thereby combining both BERT model and LSTM and memory network using an ensemble method was not possible. One more thing that we faced was like with LSTM and memory networks, we had to reduce the size of the input sentences that is passed to the model because a larger size led to a very large model and caused performance issues, and both the models were overfitting. So in conclusion, we find that like the BERT model and LSTM model, they try to find the end answers to a questionnaire for a reading comprehension, but due to the challenges of capturing the sequences and training it, the performance were degraded.